Welcome to section 13.1, Introduction to Functions of Several Variables. So chapter 13 is going to be the chapter about differentiation, and chapter 14 is going to be the chapter about integration. Section 13.1, though, doesn't really talk about differentiation yet. Objectives: understand the notation for a function of several variables, describe fundamental characteristics of two variable functions and sketch their graph, sketch level curves for a function of two variables, use computer graphics to graph a function of two variables, and understand the concept of level surfaces for a function of three variables. So an example of a function of two variables is given here. So instead of having f of x, you inform the reader on what the variables are. So here it's f of x and y. So these are the independent variables. So you can choose them and it'll give you one number as an output, which we can write f of x, y, or z equals. So here, let's say z equals pi x squared y. Just like in two dimensions, we will have a domain and a range. The range will be a number, but the domain is going to be a pair of numbers that we can represent in the xy plane. So what's the domain of f of x and y equals ln of x times y? We have to find values inside the ln that are positive. So we need x times y to be greater than 0, which means all the points in quadrant 1 and 3, not including the axes. You can therefore sketch this as well, and even though we are talking about a function that would sit in three dimensions, the domain is the first two dimensions, so it's represented by this Cartesian plane with the x-axis and the y-axis. Normally, when the border of a domain or just the border of a region is not included, we would put dashed lines to show that this border is not included. Here we can't really put dashed lines because it's right on the axis, so I added not including the axis, right? If x equals 0, that's going to be ln of 0, and that's not defined. Example B, what's the domain of that function here, which has three independent variables, and the letter we would typically choose, if we wanted to choose a letter here, we would probably call it w equals something. That would be the next choice after x, y, and z are exhausted. So we need x to not be 0, because we can't divide by 0, and we also need all of the expression inside the square root to be greater or equal to 0. So x squared plus y squared plus z squared needs to be at least 16, and x cannot be 0. If you try to visualize that domain, so now we're looking at all the points in space that yield an output, it's going to be all the points that are beyond the sphere that has radius 4, centered at the origin, but also none of the points that are in the YZ plane. So not so easy to visualize, but an interesting thing to think of. What is the range of the following function? So this time it's only one value, because the output of such functions is always just one number. So here ln of something can be any number from negative infinity to positive infinity, so the answer is all real numbers. In an example like this, the range, the outputs that are reached by the function are anything that is 3 or greater. Sketching graphs. Sketching graphs can be quite a bit complicated. It's not always easy to visualize what we're trying to show, and it's not going to be a skill that we really want to test. But thinking about surfaces in 3D and thinking of the best way we can attempt to represent them on a piece of paper with a pencil is a good exercise. So for example, when you have f of xy equals ln of 1 over xy, we are focusing on the first quadrant of the domain here, so xy are greater than 0. We may think of the trace So for what values of xy will we have an output of 0? And we know ln of 1 equals 0. So it would be when x times y equals 1. So x times y equals 1 translates as y equals 1 over x. So if for a minute you only look at the xy plane, which is the floor here, that would mean we are sketching y equals 1 over x, which is this line here. This line here. Well, it's not a line, this curve here. That would be all the points where the surface is intersecting the xy plane. And then for values of xy that are closer and closer to 0, since it's going to be 1 over a small number, it's going to be big, and ln is going to rise. Now, the function is a little bit more complicated than that. It's, from the sketch I show here, it looks like it's just hanging at the top here and then just falling down. But if you imagine what happens if we just set y equals 2, for example, y equals 2, and then we do x equals 0, so we approach like that. If we plug in y equals 2 and a value of x that approaches 0, once again, it's actually going to be a very large number. So this curtain that is falling down is actually going back up if you approach the yz plane or the xz plane. The graph of f of x and y equals 16 minus 4x squared minus y squared can be rewritten, well, the expression can be rewritten here if we take the square and we get something that we recognize eventually. 4x squared plus y squared plus z squared equals 16. That's an ellipsoid. By just looking at the intersection with the x-axis, the y-axis, and the z-axis, we can find the intersection and it will help. So it would intersect the x-axis at x equals 2, the y-axis at y equals 4, and the z-axis at z equals 4. And so we can sketch the ellipsoid. Now, notice that this is the positive square root only, so even though this is an ellipsoid, that is only the upper half of an ellipsoid. So if every time we pick an ordered pair, x, y, and we get a single value for the output of f of xy, then we call that a function. In earlier years, you may have thought of the vertical line test. It's the same. It's the vertical line test, but in 3D. So every time I draw a vertical line, I would get only one intersection. Let's just pretend it intersects the ellipsoid here. You would only get one intersection. That's a function. So an ellipsoid itself would not be considered a function. It's a relation. What are we allowed to do with the functions? We can add them, we can subtract them, we can multiply them, we can divide them. We just have to be careful if we want to compose function f of g of something. Well, the outside function, in this case it's f, you see that it's going to be a function of one variable, because g of xyz or g of xy is always just one number. We talked about that. The range of these functions is a single value. So that means function f is only f of x, or f of one variable. So you can't compose f of xy and g of xy. Well, you could, but you have to be more creative. Contour maps. So this is something we recognize from weather maps or topographic maps. It shows different altitudes or different pressures. And we are going to use the same because it allows us to represent 3D curves in 2 dimensions in a way that is sometimes maybe difficult to read, but sometimes it's going to be easier to represent a surface than to really try to sketch it. So how do we read that? If we are going up a mountain here, when there's a lot of space between these level curves, it means it's not going up so much. When it's very narrow, the space between level curves, it means the slope is really steep. So much space between level curves indicates that z is changing slowly, whereas little space indicates rapid change. Sketch the contour map of the surface given by f of xy equals square root of 81 minus x squared minus y squared. So here we are told which level curves to pick. If we weren't, we would just make a choice. So we would look at what are all the points where z equals 0, what are all the points where z equals 3, where z equals 6, where z equals 9. We just choose the best ones. And it's not always obvious, but choosing the level curve for z equals 0 is typically a good idea because it's the trace in the xy plane. So if we select f of xy equals 0 here, then we can plug 0 in, and we notice, oh, well, it's just a circle with radius 9. And if I plug f of xy equals 3, what I see is that I actually have a circle with radius root 72, and then with z equals 6, the radius of the circle is root 45, and if I plug in f of xy equals 9, well, I get a circle, between quotation marks, with radius 0. So all of these are circles, so we can represent them here roughly. What's interesting to pay attention to is that the distance here is smaller than it is here, and even smaller than it is between the last two level curves, even though our choices of z was an arithmetic sequence, 0, 3, 6, 9. So if we slice at 0, at 3, at 6, and at 9, these are the shapes of the slices we would see looking from above. So this is like looking from above, and you can see where the surface was cut. So we've talked about drawing rough sketches. It's tough, but we can try our best. In the example here, we have a contour map. We can see that these are going further and further down. It's c equals -2, -4, -6, etc. And these as well, we should assume, those here are going up. So the further I'm going along the y-axis, the higher the surface is. The further I'm going along the x-axis, the deeper the function is. This is my attempt. It's not very easy to do, but we can at least kind of see the hyperbolas here and there that are represented here and there. All right, so there's a software that is right in your MacBook. If you search and you type Grapher, it has this symbol here, and if you choose that, you can use that software. So it will offer you to graph in 2D or 3D. So for us, it's going to be 3D. We pick that. And so this is the x-axis, the y-axis, the z-axis. You can move it around. So if I say x squared plus y squared, you can see the paraboloid. And you can zoom in and zoom out. If you want to sketch another function, then you go to the plus down here, new equation. There's going to be times where it's going to be useful to do a new equation from template. A new equation that just offers you another option. Notice that it starts with z equal, but if you type x squared plus y squared equals z squared, it also gives you, there's no problem in that. It can handle anything. It doesn't have to be an explicit expression. You can change the colors if you go in the inspector. And so on. And you can kind of change the quality as well. You can make it more with a better resolution, which is sometimes worth it if you have quite a complicated function that goes up and down a lot. You may want to improve the resolution here. So let me just see what we get if we choose new equation from template. This is where you would go for a line. So since we have parametric equations for lines, you would go to curves and you would pick the first one, and the parametric equations would be x equals whatever you type here. Let me just do it. X equals t, y equals 2t, z equals minus t plus 1, and here's the line. So if we want to type the equation of the function that we are given, you will need to type in the equation. Let me do it again. I had to try first. So it's z equals 2 minus y squared plus x squared times e to the power of, and we want to open parentheses here, 1 minus x squared minus, oops, I think that was at the exponent, minus y squared over 4. So that is the function you get here. So how are you going to sketch that on your page? This is an example of quite a difficult graph to sketch. So this was my attempt. Hopefully, once we've seen the surface, we recognize that that's what it was. Finally, the concept of level curves can be extended to level surfaces for functions of 3 variables. Each value of c yields a level surface. So level surfaces is something that occurs when we have a function of 3 variables, f of x, y, z. Imagine what that means. It means we have a 4th variable, which is the output, and that is the output that I like to think as being the temperature. Imagine we are in the classroom and we have the origin somewhere, and then the 3 axes are pointing in the 3 directions in the classroom. So I can pick a point in the classroom. It will have coordinates x, y, z, and if I plug it in this function, it will give out the output, which might be 22. And let's say 22 is the temperature at that point in the room. So it's very hard to see what happens because every single point in the room has a certain temperature. So because we live in 3 dimensions, it's not easy to visualize exactly what's going on. So maybe on a graph we would use colors to show high temperatures would be red and low temperatures would be blue maybe. But anyways, we have for each point x, y, z, there's an output which we can see as the temperature. And now there may be many points where the temperature is 22. And if we only focus on those, then it will yield a surface. All the points that have the same temperature are going to be connected together. It will be continuous and it will form a certain surface. So this is what level surfaces are. I choose a certain temperature, let's say 24, and I just focus on only these points which have a temperature of 24. So now instead of every single point in space having an output, only those that are 22 will be highlighted. And we can show all those points. So let's pretend it's C1 equals 24. All the points in the classroom that have a temperature of 24 are on this surface. And maybe all the points that have a slightly lower temperature, 21, are on the cone. And maybe all the points that have a temperature of 19 are on this hyperboloid of 2 sheets here and there. So it is a way to show an output that is too big because we only have 3 dimensions to think with or to visualize as humans, so we can represent layers of that volume one at a time to kind of see what goes on.